Hello, my name is Amanda Wilson, and I'm an Environmental Health Sciences PhD candidate at the University of Arizona. My research interests include quantitative microbial risk assessment, sometimes referred to as QMRA, exposure science, exposure modeling, and human behavior. Some of my current and previous work includes studying how viruses transfer between fingertips and surfaces, estimating the contribution of portable equipment to the spread of infectious microbes in hospitals, and comparing mask materials and their ability to reduce infection risk. Today I'll be giving a brief overview of some exposure science concepts and how these apply to interactions when we're thinking about exposures in a COVID-19 context.
Hi, my name is Kacey Ernst, and I'm Professor and Program Director of Epidemiology at the University of Arizona. My research interests broadly focus on infectious disease epidemiology, including surveillance, the development of community-based interventions, and the uptake of prevention strategies. Some of my current and previous work include examining the community perceptions of control strategies, including, most recently, the Google-Apple exposure notification technology, developing a community-based surveillance application to monitor and educate about dengue, and developing early warning systems for climate-sensitive diseases. I want to start today with this slide. It serves as a reminder to all of us here of why we're doing this work and why we're so committed to developing new strategies to prevent and control the spread of SARS-CoV-2. Globally, we are over 13 million cases and have nearly 600,000 deaths of COVID-19. But we can't just look at these numbers dispassionately. These are mothers, brothers, fathers, friends, sisters, and children. How did we get here? SARS-CoV-2 was originally a zoonotic disease that crossed into the human population. Now it's primarily transmitted through close contact and droplet spread. It can also be aerosolized under specific settings and lead to airborne transmission. There's also concern that transmission can occur when surfaces or fomites get contaminated. However, this mode of transmission has yet to be rigorously quantified. Other lesser studied potential modes of transmission include mother to child during pregnancy, fecal oral transmission, which is a possibility given viable viral shed in the stool, and bloodborne transmission. All of these need much more rigorous evidence in order to define their quantitative probability. One of the reasons SARS-CoV-2 transmission is so challenging to prevent relates to the fact that it can spread before someone shows signs or symptoms of illness. This is called pre-symptomatic spread, and even when individuals will never show symptoms, and this is called asymptomatic spread. On average, the time from exposure to symptoms is 4 to 6 days, but it can be as long as 14 days. But people can spread the virus to others 1 to 3 days before symptoms begin. It's thought that approximately 1 week after symptom onset, people are less likely to transmit virus. However, it's important that ill people isolate for at least 3 days after they no longer have symptoms. There are several important factors that alter the chance of infection with SARS-CoV-2. Amanda is going to go into more details on some of these, but the duration of exposure and distance from the infected individual are two critical determining parameters. In addition, the age of the infected person may also influence transmission. Younger children appear to be less likely to transmit when infected. Growing evidence of the benefits of masks has led to many policies worldwide to encourage or mandate mask wearing. Being face-to-face as compared to side-to-side increases exposure, and being indoors is much riskier than outdoor exposures. In addition, respiration patterns, exercising, singing, coughing, sneezing, or other activities that increase the force of exhalation increases the potential for aerosolization and expulsion of virus into the air. The strength of evidence is still building for some of these factors, but they are all important. As an epidemiologist, I see the potential in Bluetooth exposure notification technology. It has the potential to be faster, notify people that you don't know, preserve privacy, minimize recall bias of duration of exposure, and has the potential to connect well with public health guidance and provide resources to people that may need to be in quarantine. In addition, the Google-Apple partnership places a high level of emphasis on partnering with public health agencies to ensure congruency with applied public health policies, which is extremely important in an era of ever-expanding mixed messaging that confuses the public. Even though uptake of these technologies is unlikely to be universal, there are specific use cases that maximize exposure notification technology utility. This includes instances where there is a high chance for interacting with people you do not know. This could include large classes in university settings, public transportation, or during travel. And then also places where marketing can be explicit and encourage uptake, such as large workplaces or universities. And then also in regions where manual contact tracing programs are delayed or overwhelmed. In these instances, automatic notifications may sadly be the only timely way that notification of exposure is being received. Despite the promise to these technologies, there are obvious challenges as well. Ensuring high uptake is critical, not only because we want to enhance the utility of the technology, but also we want to minimize the chance for false senses of security. Say you have an individual who's not getting any exposures. If it is because there just aren't people around them that have the app, this may lead to a sense that they're okay, that they are not ever being exposed, and that could be a dangerous thing. In addition, the technology is challenged by equity issues. There are huge disparities in transmission of SARS-CoV-2, and smartphones are still out of reach for many community members. Or they may have older technology that just has poor performance. Individuals who have the means to use the apps may already be those who have the luxury to stay at home. So identifying ways to overcome this inequity is absolutely critical. In addition, the availability of testing could limit its utility, especially if clinical diagnoses and positive laboratory tests are required in order to send out an exposure notification. In these instances, like we have currently in Arizona, where laboratory results are taking 7 to 14 days in order to get back to people, there is limited utility in the application, which relies on positive tests as the means to send out exposure notifications. And finally, it could be challenging to put into place physician-generated codes for input into the app for case confirmation. That infrastructure and buy-in that we would need from the medical community is quite significant. All of these are really complex issues and will require strong collaboration and interdisciplinary efforts to maximize the benefit of the technology.
Now that Dr. Ernst has given a great overview of COVID-19 and how digital contact tracing fits into that, I'd like to talk about exposure science and how we go about determining the risk of a single exposure. A good place to start when we're thinking about risk is dose. In this case, dose is usually the number of microbes that we're ingesting or inhaling, and in this case, we're looking at a number of viral particles. Dose affects our risk of a negative health outcome. Some of these health outcomes might be infection, illness, or death, or sometimes they might be microbe specific. A relationship between dose and the probability of a health outcome is referred to as dose response, and this usually takes the form of a sigmoidal curve shown on the left. You'll notice that with microbes, this relationship usually involves dose on a log scale. So on the x-axis, we have dose in log units, and you might be thinking, what is a PFU? A PFU is a plaque-forming unit. So that's similar to CFU for bacteria, colony-forming unit, but PFU indicates that we're talking about viruses here. On the y-axis, we have the probability of the response, which in this case is illness. And this is a curve that was actually fit to data for coronavirus and looking at SARS-CoV-1 specifically. So not SARS-CoV-2, the one that we're interested in for COVID-19, but it at least gives an example of what these curves look like for different microbes. In our previous slide, we saw that dose was important, especially when we're using a risk-based approach to look at different interactions. So the next logical question is, okay, what affects dose? One of the key parameters that affects dose is time. So this is a really simple example, just sort of showing why time is important, especially for inhalation exposures. People inhale air at a certain rate, cubic meters per second, and so if we know how many seconds you're inhaling air, we can look at the total volume of air that you inhaled. Then if we have information about the amount of virus that's per cubic meter or per volume, we can look at the total amount of virus or the dose that you inhaled over that period of time. So as the duration increases, the volume of air that you inhale over that time increases, and the amount of virus you inhale over that time increases. Another component to consider when we're trying to estimate dose is the orientation of the faces of the people who are interacting. So even if we're in close proximity, we may not always be facing each other, and other times we will be, and that influences how much virus we could potentially be inhaling in our inhalation range around our face. And there was a great study by Zhang et al. In 2019 where they looked at how often people interact in different distances and what the orientations of their faces were during those interactions. And this was within the context of a graduate student office, but I think this study offers really great insights for thinking about this type of influence on interactions and doses in other scenarios as well. Connected to the idea of orientation of faces and its effect on dose is the distance between people. Bigger droplets that potentially contain more virus than smaller droplets will deposit faster over shorter distances, meaning that closer interactions pose greater risks to be exposed to these larger droplets. Aerosols of smaller sizes can also contain virus and also pose risks, but in terms of distance, we're really looking at how these aerosols might be dispersed throughout the air and how quickly they may deposit on surfaces. And this happens over very small timescales. So these figures on the left are from a computational fluid dynamics study. And in the top figure, we're looking at 0.25 seconds of an emission from the person on the left. And in the bottom, we see after 1 second, a lot of those larger droplets have already settled out. And so looking at how close we are to someone and whether we're going to be exposed to those larger droplets is an important piece in determining someone's risk from an interaction. Another important piece of understanding dose is understanding the amount of virus that's being shed during those emission events, like was shown in the figure in the previous slide. On the left, we see a theoretical idea about how shedding occurs over time relative to when someone's symptoms begin. On the right, we see a similar comparable figure, but this is showing real-world data. So on the x-axis on the figure on the right, we have days from first evidence of symptoms, which in this case they were focused on fever, cough, or shortness of breath. And on the y-axis, we have cycle threshold value. A cycle threshold value indicates how many replications were needed in a molecular process to see something, to be able to detect the virus. So what that means is a larger cycle threshold value basically relates to a smaller amount of virus. But when we're using a molecular method, what we're really detecting is RNA of the virus, not necessarily infectious virus. So this figure on the right is really helpful because it's showing not only cycle threshold values that give us some indication of the molecular detection, but they also show us culture methods that measure infectivity. And we can see that we don't see this beautiful curve like we see on the left. So when we're evaluating different mathematical approaches for understanding or estimating the amount of virus someone might be shedding based on their days since symptom onset, it becomes really challenging to sort of marry our theoretical ideas with the data we see. Another piece to detangle is the characteristics of the air and how that impacts dose. One of the big areas of debate or things that everyone is talking about is indoor versus outdoor exposures. And I really like this analogy from Lindsay Marr. She's a well-respected scientist, she's very active on Twitter, and she has really great ideas for communicating these concepts to the general public. And I really like this metaphor in this tweet. She said, indoors equals putting a drop of dye into a glass of water. Outdoors equals putting a drop of dye into the ocean. So thinking about the approaches we use for mitigating or decreasing risks for indoor exposures becomes really, really important. But she does emphasize it's still important to maintain distances outdoors. But indoors, we can see that the risks are likely higher. Another piece to the puzzle is the characteristics of the air or the environment where these exposures are happening. So something that's really of interest to me is relative humidity. And maybe that's because I live in a very arid environment, so I'm hyper aware of humidity when I go to other places. But relative humidity has effects on not only dynamics in the air, but also dynamics on surfaces. So we know that we see greater transfer efficiency, or the fraction of total amount of microbes that are transferred from one surface to another upon contact, for higher relative humidities. So in a higher relative humidity situation, if you touch a surface and you have microbes on your hands, you're likely to transfer more microbes to the surface than if you were in a low relative humidity environment. We also know that relative humidity has effects on inactivation of viruses on surfaces and in air. And we know that it has effects on aerosol sizes. So we can see in the figure on the right that as the relative humidity goes up, the concentration over time starts to go down faster because under higher relative humidity conditions, you have less evaporation from the aerosols. They maintain a larger size for a longer period of time, meaning they drop out faster. So this has a lot of important implications for understanding exposures. And some people might say, okay, so what are you telling me? Are you saying relative humidity should be high or should be low? I think it depends on whether you ask someone who studies aerosols or someone who studies fomites, but the main takeaway from this is that it affects both. So to sum things up, what makes one interaction riskier than another? The following question should probably be answered to inform that. How long was the interaction? How close was the interaction? Do we have any information about orientation of faces? How much was the person shedding during that interaction? And what were the characteristics of the air where this took place? Thank you very much for your attention today. Here are my references if you're interested in looking into more of the details. And I've also provided our contact information if you'd like to reach out for more questions or discussion.